Hey guys, we're back today with my good friend Matt the Laxative Mashad, and today we're going to be doing a few more physics problems.
It's going to be a
Matt,
real hoot and a holler, I tell you what.
yeah, exactly. Go ahead and read this question out loud, Matt.
You got it. So, a baseball pitcher throws a baseball with a speed of 43 meters per second. Estimate the average acceleration of the ball during the throwing motion. In throwing the baseball, the pitcher accelerates it through a displacement of about 3.5 meters from behind the body to the point where it is released.
Awesome. So yeah, Matt, what are we actually solving for in this question? What is the unknown?
The unknown is the acceleration between the ball being pitched from the beginning of the throw to when the ball is released. So it's not the acceleration of the entire pitch, it's just during this throwing motion.
Perfect. So we're finding the acceleration. Do you know the initial velocity here?
The initial velocity is 0.
Do you know the final velocity?
The final velocity is 43 meters per second.
Nice. And what other information do they give us?
We also know that the displacement of distance of the pitch is 3.5 meters.
Awesome. Okay. Do you remember the kinematic equations?
Yes. V final equals V initial plus acceleration times time.
Nice. How about the second one?
Let's see.
Oh,
Delta X equals V final plus V initial divided by 2 times time.
oh, nice. Yeah, that's a different one. V final plus V initial over 2 times time. V final plus V initial over 2 is the average velocity. However, we're not actually going to use this one. I just don't consider it in the three primary kinematic equations. We'll make that a fourth down here. This one is going to be V initial times time plus 1/2 AT squared. However, we can put that one off to the side. It's not a bad one. I just don't consider it in the three primary kinematic equations. Delta X equals V final plus V initial over 2 times time. Do you remember the third kinematic equation?
No.
So this is going to be V final squared equals V initial squared plus 2A delta X. Now, which of these three equations should we be using to solve for the acceleration, given the information that we have?
I think we should use number 3.
Yeah, number 3 makes sense to me. Can you help me fill it in?
43 meters per second squared equals 0 plus 2 times
A is our unknown, right?
A is our unknown times 3.5.
Nice. All right, now we just have to do algebra to solve for the acceleration, right?
Right.
Let's begin rearranging this. What's the first thing I can do here, Matt?
First thing we can do, can we divide each side by 2?
Yeah, we can divide each side by 2 and 3.5. So we get 43 squared over 2 times 3.5. And actually, we're ready to solve this. Go ahead, pull out your calculator, and we're going to do 43 squared divided by, open parentheses, 2 times 3.5, close parentheses. And let me know what you get for your answer.
My answer was 264.1.
That's what I got. What are the units?
Meters per second.
Meters per second squared, because it's an acceleration.
Okay.
Nice. Great stuff. How you feeling about this problem?
I feel good.
Yeah, you understand it?
Yes, I see that we had to use the equation where we only had one variable missing. We didn't have time, and the other equations had time, and it would have been a lot harder to solve this if we needed time to finish the problem.
Nice, perfect. So this problem's not too complicated. We could do it with a single equation. We had all of the variables except the unknown, which is ideal. Perfect. Great stuff.
A fugitive tries to hop on a freight train traveling at a constant speed of 5 meters per second. Just as an empty boxcar passes him, the fugitive starts from rest and accelerates at 1.4 meters per second squared to his maximum speed of 6 meters per second, which he then maintains. How long does it take him to catch up to the empty boxcar? What is the distance traveled to reach the boxcar?
Perfect. Matt, I'm going to expect that voice to maintain through this entire video.
No problem.
What are we solving for here?
So it's in two parts. So we're solving for time for A, and we're solving for the distance traveled for B. And we're probably going to have to solve in that order to get each answer.
Let's talk about this a little bit. Our fugitive is catching up to this train. They're starting at the same place, and the train is going at a constant 5 meters per second. The fugitive starting from rest. So initially, that train is going to get a bit of a head start, but then the fugitive is going to start accelerating until he catches up to the train. So we want to solve for the amount of time it takes for the fugitive to catch the train. Let's start with that in part A. So I've put a little drawing here. Our train is starting. It has a constant velocity, meaning v initial and v final are equal, of 5 meters per second. We can also state, but we don't have to, that its acceleration is equal to 0 meters per second squared. Now we have our fugitive starting with 0 meters per second velocity and accelerating at 1.4 meters per second squared. They're both starting at the distance is equal to 0, time is equal to 0. Let's start with our fugitive. How long is it going to take for the fugitive to get from 0 meters per second all the way up to 6 meters per second?
We're solving for time.
We are.
Do we not know that yet?
We don't know how long it takes to go from 0 to 6 meters per second for the fugitive, but we can solve it.
Could we use v final equals v initial plus acceleration times time?
Yeah, let's try
for
that. V final equals v initial plus at. What's the final velocity that we're considering here?
The final would be 6 meters per second.
Nice. We have 6 equals the initial 0 plus the acceleration is what?
1.4 meters per second squared.
Nice. Go ahead and solve for that time. I'm going to call this time t1 because it's the amount of time he takes to get up to speed. So this is going to be 6 divided by 1.4.
And I got, is time 4.29 seconds?
Yeah, perfect. 4.29 seconds. Let's see how far he travels in those 4.29 seconds. So now we have time, we have initial velocity, we know the acceleration. How can we calculate the fugitive's distance covered in that time?
So we know in 4.29 seconds, he is moving 1, and I forget the unit, but we know the train is moving at a rate of 5 meters per second.
Oh, so what you're saying is that now he's moving 1 meter per second faster than the train.
And that's how we'll know when he's caught up, is we have to know the train is going plus 5, plus 5, plus 5. And then he will accelerate to this rate of 6 to the point where he'll eventually catch up with them when we add this all together. So
exactly.
It's tricky, but yeah, it's not. Yes, it's tricky.
Good call. So what we're going to do first is we're going to make sure that he hasn't caught the train by the time he's accelerated to 6 meters per second. Now, we can mostly assume this to be the case, but let's just verify it using our methods. I'm going to use the second equation, delta x equals v naught t plus 1/2 a t1 squared. This is going to give us the distance that the fugitive travels while he's accelerating, or she. I don't want to make any assumptions here. Delta x, what's the initial velocity of the fugitive?
The initial velocity of the fugitive is 0.
0. What's our time?
4.29 seconds.
Right. Doesn't really matter for this part because it gets multiplied by 0 anyway. Plus the 1/2, 1.4, that's our acceleration, times 4.29 squared. Can you calculate the distance that the fugitive travels in this time? 0.5 times 1.4 times 4.29 squared is what I'm doing on my calculator.
I got 9.2.
I didn't get that. Could you tell me exactly what you typed in?
I put in 0.5 times... Oh, I typed it in wrong.
That's okay, that happens.
I put in 1.0 instead of 1.4. I'll try that again.
Gotcha. This is why we check. A lot of times I'll be doing problems and I'll get something wrong, and it's always just the silliest mistake.
This time I got 12.89.
That's what I get. So 12.89 meters. Let's just verify that he hasn't caught the train by calculating how far the train traveled in that same amount of time.
Okay.
So this is delta x for the fugitive. We're gonna do delta x for the train. Matt, what equation should we use here? Or how should we fill in our second kinematic equation to solve for the train's distance?
So we have the distance that the fugitive traveled.
Right.
And we're trying to find how far the train traveled.
Yeah.
Is it possible to do this same equation again, but then plug in what we know about the train instead of the fugitive?
Yes. Go ahead and start that. Let me know what I should plug in for V naught, V initial.
Okay, so the V initial for the train doesn't start from rest.
Mm-mm.
The train starts at the constant speed of 5 meters per second.
Perfect. And how much time are we taking for this train? We're testing it over the same amount of time, right? To see how far it travels.
Okay, so we can put the same time that we had plugged in before.
Exactly.
That would be 4.29 seconds once more.
Plus 1/2. What is the acceleration of the train?
So the train's at a constant speed. It's not accelerating.
Yes, that's huge. So notice here, constant speed means acceleration is 0. That's a trick that they're going to throw into a lot of problems that not everybody sees their first time through.
And then we put in 4.29 again, squared.
Right. And really this whole second half, we don't have to do any calculations because it just gets multiplied by 0.
Right.
Let me know how far the train travels, Matt.
Would that be 21.45 meters?
Yes. So, did they travel the same distance?
They did not.
Right. That's a good way to verify that we have to expand this problem a little bit. This is where it gets a little tricky. So, our fugitive, his total distance covered is going to be something like this. We know that from here to delta x, from starting to 6 meters per second, it's going to take him 4.29 seconds. So we have to get that the delta x of the fugitive is equal to the delta x of the train. What we're going to do for this is the delta x of our fugitive, it's going to be v initial t1 plus 1/2 a t1 squared. But then once he gets up to that speed, we're going to have a new initial velocity. We're going to call this v naught prime. And v naught prime is equal to 6 meters per second. Or in other words, it would be his v final from the previous one. And that is going to be multiplied by t2, some new time. All of this is going to be equal to the train, and the train's velocity is constant. V naught train, I guess I should call this v naught fugitive and v naught prime fugitive, times t1 plus v naught train times t2. This is pretty tricky. We can do this because this entire umbrella here falls under the distance traveled by the fugitive. First, whenever he's getting up to speed, and then when he's moving at constant speed. The second part is the train moving at constant speed for time t1, and then continue to move at that constant speed for time t2. So this falls under this umbrella of the distance traveled by the train. And we know they're going to be equal.
So this is my first exposure to V naught prime and these labels.
Yeah.
So I can't pretend that
It's tricky,
I fully
right?
understand it yet. This is my first exposure to it. Are these labels that we designate to help organize the problem? Or is this a whole new equation?
This is actually something kind of separate. You don't have to memorize these labels. This is something that I'm coming up with in order to give meaning to these variables. All I'm doing is I'm differentiating the initial V naught from the final V naught.
Oh, so this isn't a new equation. This is just something you're using to understand what each thing is when you're solving.
Exactly.
Okay.
And there are multiple ways to do this problem. I decided to put it into a giant equal equation here. We know that they have to travel the same distance. And so we know that the distance traveled by the fugitive is going to be the acceleration distance plus his constant velocity distance whenever his velocity is 6 meters per second. For the train, it's going to be the constant velocity for time t1 plus the constant velocity for time t2. So it turns out what we're solving for here is just t2. This is going to make more sense. Let's continue with the process. So the initial velocity of our fugitive is 0 when they start. T1 is 4.29 plus 1 half 1.4 times 4.29 squared. We already kind of did that, so we know that this part's going to be 12.89 meters, right? This is what we did in part 1 here. Now, we have to add 6 meters per second, because that is the velocity that he gets up to, times t2. And t2 is what we're going to be solving for here. This is going to be equal to the velocity of the train, which is 5 meters per second, times t1, which is 4.29, plus the same constant velocity of the train, times t2. Now, this is a lot to look at. Immediately, I'm going to simplify it. We know that this whole section is equal to 12.89, because we solved that earlier up here, plus 6t2 equals, what was 5 times 4.29? We solved that before, right?
Oh, that is 21.45.
Plus 5t2. This is solvable, isn't it?
It is.
I'm going to start by subtracting 5t2 from both sides, and I'll subtract 12.89 from both sides. Okay, 6t2 minus 5t2. What is that going to be equal to?
1t.
Yeah, or just t2.
There we go.
6 minus
so
5
we've
is 1.
isolated it.
Yeah, we did. And this actually worked out really nicely. We don't have to do any division after this. Pull out your calculator and go ahead and do 21.45 minus 12.89. Keep in mind, these just cancel out. That's the whole point of subtracting those numbers.
8.56.
Perfect. That's what I get. 8.56. What's the unit?
8.56 meters.
It's time.
Oh, it is time. Okay. Seconds.
Seconds. There we go. Now, is this the total amount of time that it takes the fugitive to catch the train?
No.
How do we get the total amount of time?
Isn't this time just the time it took to get to the rate of 6 meters per second?
No, that was T1.
Oh, that was T1. Okay.
This is the time it takes from whenever the fugitive gets to 6 meters per second to then catching the train.
Okay.
So we can add them together. I'm going to put this in a circle because it's not the final answer. So our total time, I'll just call it T, is equal to T1 plus T2. So we have it being 4.
Oh, so T1 was 4.9.
Yeah, exactly.
Okay, so we have that.
Go ahead and calculate the total time.
That would be 12.85 seconds.
Nice. Awesome. Is this making sense?
This was one of the hardest ones, I
Yeah,
think.
not an easy question at all.
Yeah.
So, if anyone is watching this, this is not the only way that you can solve this problem. Let us know if there's another way that you could figure out how to solve this, and maybe if you can solve it easier or faster. And also, make sure to remember this kind of math next time you're trying to hop onto a moving train.
Oh, brother, where art thou? A stone is dropped from the top of a cliff. It is seen to hit the ground below after 3.55 seconds. How high is the cliff?
Okay, what do we know here?
We know that the initial velocity would be 0 because it's being dropped from a place.
Right?
And we also know that the force of gravity is acting on it, and that would be Negative 9.8.
Nice. And we know that the time is 3.55 seconds.
Yeah.
We are looking for delta x, the change in position, or the change in height. If you want to call this delta y, that's also an option. What equation can we use that's going to help us solve for delta y using these other variables?
So we could use delta y equals initial velocity times time plus 1/2 times acceleration times time squared.
Nice. Let's go ahead and fill this in. Delta y, what's the initial velocity?
0.
And the time's 3.55, but I'm not even going to put that because anything times 0 is 0, plus 1/2 times negative 9.8 times 3.55 squared. Can we solve this on our calculators?
We can.
Let's do it. I'm not going to even include the 0 times 3.55 because I don't need to. I'm going to do 1/2 times negative 9.8 times 3.55 squared. Now, if you come up with an error when you're doing that, make sure that there's usually a negative button and a minus button, and those are two different things on your calculator. Matt, what did you get for your answer here?
I got negative 61.75 meters.
This is the distance that the rock falls. Now let's note here, the final, y final is going to be the bottom. It's going to be equal to 0 meters. Y initial is the top. We have delta y equals y final minus y initial. So if we want to get y initial, we just solve like this. Negative 61.75, that's delta y, equals 0 minus y initial. And we get that y initial is 61.75 meters as the initial position. Position versus distance. Similar, but different things.
Pardon me.
Bless you. Awesome. Let's go on to part 2, or number 40, I should say. This is a completely different question. It has nothing to do with number 39. Go ahead and read this one, Matt.
Estimate how long it took King Kong to fall straight down from the top of the Empire State Building, 380 meters high, and his velocity just before landing.
Awesome. I tried drawing the Empire State Building and I failed miserably, so I'm drawing a rectangle. So we have that delta y is 380 meters. We want to calculate time and final velocity.
Could we use delta y equals initial velocity times time plus 1/2 of at squared and solve for the missing variable that way?
Let's try it. What is the acceleration going to be equal to?
Negative 9.8.
Perfect. What is the initial velocity equal to?
0 once more.
Perfect, because he's falling, and so he didn't jump down or jump up at the beginning. And we want to find time. Go ahead and plug these in to solve. So we get negative 380 equals 0 times time. That cancels out. Plus 1/2 times negative 9.8 times t, which is what we're solving for, squared. I'm going to do a little bit of algebra. This just goes away. We don't have to worry about it. Negative 380. Multiply both sides by 2 to get rid of that 1/2. And divide both sides by negative 9.8. Not 9.t. 9.8. That's going to be equal to t squared. If we want to solve for just t, we take the square root of all of that. 380 times 2 over 9.8. Notice I got rid of the negatives because a negative over a negative is a positive. If you put this in your calculator, make sure it's all in parentheses inside the square root. Matt, let me know what you got for this answer.
I got 8.8.
Nice. What's the unit?
The unit is 8.8 seconds.
Awesome. That is our time. Now the second part is asking for the velocity just before landing. So we have a second unknown, v final, but now we know our time.
What I think we can do here is we could use v final equals v initial plus acceleration times time now that we've solved for the missing time variable.
I agree. Let's go ahead and use this to solve. V final equals 0 minus 9.8 times 8.8. Let me know what you get.
Would it be negative 86.24 meters per second?
Yeah, awesome. Our final velocity is going to be going down at 86.24 meters per second. Good stuff. Do one of those virtual high fives through the camera.
Two students are asked to find the height of a particular building using a barometer. Okay, they're confused, but they got the spirit. Instead of using the barometer as an altitude measuring device, they take it to the roof of the building and drop it off, timing its fall.
The Weather Service reports that barometers are falling sharply. Oh no!
One student reports a fall time of 2 seconds and the other 2.3 seconds. What percentage of difference does the 0.3 seconds make for the estimates of the building's height?
Yeah, no, I don't think they're confused. I think they know how to use a barometer properly.
I think these students are like me before I met you. I'm feeling a kinship.
Yeah. Barometers are meant to measure pressure, by the way. So it would have been a struggle to measure the height of the building with pressure anyway. Doable, but pretty tough.
And I see that the barometer just kind of throws us off. They could have dropped anything to make this claim or prove this. It could have been a basketball, a package of vanilla wafers, but they chose a barometer because we're going to think about air pressure while reading the problem.
Two students are asked to find the height of a particular building using a measuring tape. They decide to drop it off.
It's that number 78.
All right, let's get into this. What do we have? What's known?
So each student recorded a different time when the same item was dropped once.
Yes. So we have building and same building. And for this one, the time it took to fall was 2 seconds. And for this one, the time it took to fall was 2.3 seconds. Correct me if I'm wrong. That seems correct. That seems to be all the information they've given us. But what else can we conclude, given that we know certain things about how things fall?
So we could work gravity into it.
Right. Gravity equals, let's put 9.8 meters per second squared. Do we know anything about the initial vertical velocity?
That would be 0 to start.
Yes. V naught vertical equals 0 meters per second. Perfect. Do you think we can solve for the distance it falls from here? I'll write down our kinematic equations. Number 1, V final equals V initial plus AT. Delta x equals V naught t plus 1/2 AT squared. And delta x can always be replaced with delta y. V final squared equals V initial squared plus 2a delta x. The last one is average velocity.
Would we use number 2, delta x equals initial velocity times time plus 1/2 of acceleration times time squared?
Let's try it. Let's do it for the first one. So we're actually trying to solve for the height it falls, so delta x is just fine here. What is the initial velocity?
The initial velocity is 0.
Perfect. So I won't include that velocity times time. What's the acceleration?
That'll just cancel out.
Exactly.
Then we would have 1/2 times. Will we do negative 9.8 or can we just do 9.8?
We could just do 9.8. We know that it's going to be falling down. So if we want, we can consider the down direction to be positive here. And that can work out. Let's go ahead and plug this into our calculators. 1/2 times 9.8 times 2 squared.
For that, I got negative 19.6.
Perfect. 19.6 meters would be the height of the building, according to this person's drop. Now we have the second one. It's going to be really similar, but instead of the 2 squared, we're going to replace it with 2.3 squared. Let me know what you get for this one.
For this one, I got negative 25.92 meters.
Nice. 25.9 meters. Okay, that was pretty easy. Now what are they actually asking for?
What percent difference does the 0.3 seconds make for the estimates of the building's height? So we have two different heights here. Could we subtract from them from each other
Yeah,
to find that difference?
absolutely. So we have 25.9 minus 19.6, and we want percent difference. So I'm going to divide this by 19.6.
But you're going
Because,
to divide it, not subtract?
well, no, we do both. So we subtract it to get the difference, and to get the percent difference, we divide it by one of the values.
So when I subtracted, I got 6.3.
Perfect.
So then after that step, you want me to divide 6.3 by each one individually, or just one of them in particular?
Just one of them for now. We can say that it's the percent difference from, we'll call this the original height. The 2 seconds could be the original.
When I divided by 19.6, I got 0.3%.
Nice. I got the same thing. So because I got 0.32, I'm going to call that a 32% difference. Because to get a percentage, you multiply 0.32 by 100. And I just misspoke difference and misspelled it. Making sense?
Don't feel bad. These kids dropped a barometer off of a roof.
That's true.
We're all just doing our best.
To be fair, it's probably an easier way of getting the height than it would be to measure the pressure from the ground and at the top of the building. Because the pressure difference wouldn't be that great.
That's true.
So I don't know. Those kids had that was a high IQ move. Assuming that the difference in time of the barometer falling wasn't because the first time it fell, it completely shattered, and the second time they were really dropping pieces of barometer that floated down.
And it's
So that's-
interesting, they dropped the same thing from the same height, and there was a 32% difference.
That's
I'm
a
wondering,
huge
like,
difference.
did one student drop it with his hand held high, and the other person dropped it from the top of the building, but not any higher? I'm wondering if that was the
Maybe-
margin for error.
Maybe one kid chucked it down. Let's look what a barometer looks like to see if these kids should have been dropping a barometer at all. So they look like they tend to be glass.
And it's funny, when I was picturing a barometer, I think I was picturing a metronome, like a triangular structure that would tick and talk. So
Here's what
clearly
I'm
we all
thinking.
have a lot to learn.
I'm thinking the first student dropped it off, and the second student went down with a dustpan and gathered the bits and kind of floated these off, and they kind of sprinkled down to the ground and took a lot longer.
Wait a minute. They only came to the building with one barometer. So that's
Yeah.
exactly what happened. If there were two drops, then the second drop would have just been pieces.
That's what I'm thinking.
Okay. Because when I first read the problem, I thought they dropped one barometer and each student calculated it differently. But I think there were two drops.
And barometers are not that cheap. I mean, the cheapest one online I can find is about $13.99. I'm assuming it's not this digital barometer, but even so.
Was it safety reasons? No one's ever been killed by a falling barometer, but if they had dropped a cinder block or a brick, there was more risk involved?
The teacher went to the students and said, "This is my Dalvey barometer. It's something that my dad passed down to me. It's very valuable." And they took it and they chucked it off the roof.
They go to their science teacher, "Can we borrow a barometer for an experiment?" And they drop it off a building.
We need it for a scientific measurement. Oh, man.
Oh, student's so proud of his kids. He comes back with the pieces of barometer left. Thank you.
Well, we got this figured out. All right. Thanks, Matt.
Suppose you adjust your garden hose nozzle for a fast stream of water. You point the nozzle vertically upward at the height of 1.8 meters above the ground. When you quickly turn off the nozzle, you hear the water striking the ground next to you for another 2.5 seconds. What is the water speed as it leaves the nozzle?
So, what are we looking for here specifically?
We're looking for the initial velocity of the water leaving the nozzle of the hose.
Right. And what are we given?
We are given the height of where the hose is above the ground, where the
Right.
water will leave from. We hear the water striking the ground next to us for another 2.5 seconds. So I think that's like the initial contact of the water after it's gone up and down and hitting the ground, and also for how long it continues to fall there, showing like how much water was let out of the hose.
Right, agreed. So we're looking for the initial velocity we're given. We know that acceleration is negative 9.8 meters per second squared, right? Because it always is in the air.
Oh, so yes, we have the force of gravity as a number we can work with.
Perfect. Why not? I'm calling it why not because it's the initial height.
Why not?
Is 1.8 meters. Y final is 0 meters, and our time is 2.5 seconds. Now, can you think of which kinematic equation is going to help us solve for this? I'll write them all down. V final equals V initial plus AT. Making this one delta Y since it's vertical. It's the same as delta X equals V naught T plus 1/2 AT squared. V final squared equals V initial squared plus 2A delta Y. And delta Y equals V final plus V initial over 2 times time.
Wouldn't V final equals V initial plus AT be the right way to go?
It's pretty good. Do you want to try it out?
Sure.
Okay. So we have V final equals V initial plus AT. How should I start filling this in?
Start with 0.
0 for what?
V final.
Is V final actually 0? V final is going to be the velocity as it hits the ground.
Oh no. Okay.
So we don't actually know V final. However, you're thinking of V final at the very top, which is a good thought. But we don't know the amount of time it takes to get to the top. So we don't actually know V final at the bottom here. Let's try a different one maybe.
So all these contain V final and V initial.
Not all of them. There's one that doesn't contain V final.
Oh, is that number 2?
Number 2, exactly. So we have delta Y, and I'm going to rewrite delta Y as Y final minus Y initial, because that's what delta Y means, equals V naught T plus 1/2 AT squared. And yeah, let's begin to fill this in. We have that Y final is 0, Y initial is 1.8. We're solving for V initial. We know the time is 2.5. We have negative 9.8, and then 2.5 squared. That was a real close cutoff there. Let's begin to simplify this. What's 0 minus 1.8?
Negative 1.8.
Nice. And then we have 2.5 V naught plus, and then I'm going to actually do minus here. What is 1/2 times 9.8 times 2.5 squared? It's definitely a calculator question.
So I got rounded negative 30.63.
Perfect. Now, how should we do the algebra from here? What's my next step?
From here, could we divide each side by 2.5?
We could, but we'd have to divide 1.8, 30.63, and this by 2.5. So I think if first we add 30.63 to both sides, it's going to simplify things a lot more. Well, actually, let's do your way, just to make sure that people know that they can do it, because it is an option. It's technically correct.
Sometimes my genius it's almost frightening.
So we're dividing both sides by 2.5. So on the left side, we have negative 1.8 divided by 2.5, and we get negative 0.72 equals 2.5 V naught divided by 2.5 is just V naught, and then 30.63 divided by 2.5, we'd have minus 12.25.
We could add 12.25 to the other side.
Perfect.
And then we would get our answer that way.
Yes. Let me know what you get for the final answer.
I got 11.53.
Yeah, nice. Same here. Great stuff. Yeah, that's it for this one.
So I'm just curious, did we solve the problem, or did we solve a part of the problem that we can plug in to solve another part of it?
We actually solved the problem. What is the water speed as it leaves the nozzle?
Oh, so we had enough to go off of for that then.
Yeah. So this problem is level 2 difficulty, and we're used to doing a lot of level 3 difficulty problems.
Oh, I see. So we took the bull by the horns then.
Exactly.
Okay.
Couldn't have said it better myself. Good stuff. And we're back with Matt the Muscle Mashad. Matt, can you read number 55 up to part A?
Figure 2 through 42 shows the velocity of a train as a function of time. At what time was its velocity greatest?
Okay, so this is a velocity versus time graph. How do you determine the maximum velocity?
Is it the x-axis, where it goes up like this? You could see the highest point in the green line.
Yeah, what time does that approximately occur at?
I would say about 48 to 49 seconds.
Yeah, good stuff. So this one's pretty straightforward. You literally just look for the highest points on the graph because it's a velocity versus time graph. Part B, during what periods, if any, was the velocity constant?
I would say from about 89 to 108.
Yeah, good stuff, because it's a completely flat line, right?
Yeah, flat line there.
Nice. During what periods, if any, was the acceleration constant?
It looks like the acceleration was constant from about 0 to 47.
Yeah, any other times?
It's possible that the deceleration was constant from about 52 to 77, but the line is a little more curved there. I wonder, it doesn't look as flat. Do you think that would still be a constant deceleration?
That's a pretty good answer. So that's the key here. We're looking for any time that we have a completely flat slope. Acceleration is represented by curvature, right?
Yes.
Yeah, perfect. And so any time that it is a flat slope, we're going to be having a constant acceleration. From 0 to about 40 seconds, it would be positive acceleration. And yeah, from maybe like something around like, I think it's pretty flat from about 70 to 77. You know, there's no curvature there. So we can consider that to be a constant negative slope. There's one more period of time where things seem to be pretty flat. What is that?
Well, I would say 90 to 108, but that's at a constant. So it's not
Yes.
accelerating or deaccelerating.
Yeah, exactly. The acceleration would be 0, right?
Yeah.
Right, and that is considered a constant acceleration because it stays at 0 during that time. When was the magnitude of the acceleration greatest?
Would that have been from about 108 to 121?
That would be a pretty good consideration there. What we're looking for here is whenever the slope or the magnitude of the slope is greatest.
Oh, so the highest point.
Not the highest point, the greatest slope. So whenever it's like this, that's the least magnitude of acceleration. Whenever it's like this or like this, we have the greatest magnitude of acceleration. Magnitude means absolute value, so it doesn't matter if that slope is positive or negative as long as it's steep.
Okay, would that be about 89 or 90 then?
Definitely not 90, because at 90 it's flat.
Okay. So like 88?
I would actually say probably at about 70. 70 is where it's the steepest.
Okay.
Do you see what I mean by that? We're not looking for the greatest curve, we're looking for the greatest slope, the rise over the run. So, for example, we know that at approximately 50 seconds, the acceleration is close to 0. Because if we drew a tangent line across that slope, it would be pretty flat. Then it starts to dip down, and once it gets to about 70, maybe a little past 70, it's very steep in the downward direction. That means that we have a negative acceleration of high magnitude. So, for example, if at 50, it is 0, and then at 60, it's like -1, and at 70, it could be like -1.5, and then it starts to ease back to being flat. Those are all approximations, by the way. I'm not doing actual calculations here.
Okay.
So the other contender could be around maybe 110, where that slope is again pretty steep. Now it's in the positive direction, but we don't care about positive or negative because we're looking for the magnitude. So we're just looking for the steepest slope.
Okay, so the angle is
Yes.
the best place to start. The angle of the slope.
Exactly. And that's why it's not from 0 to 40, because from 0 to 40, it's just not as steep as it is around 70 seconds.
That makes sense.
Awesome.